I did a PhD in electrical engineering. Right after that, I did a couple of postdocs for the project called ITER. There I became sort of an expert in superconductivity. I decided to go in the medical industry, where they needed help designing superconducting magnets for MRIs. My heart was really into fusion, and that's when I came across Helion. And I was really intrigued by their technology, especially the direct energy capture, which to me made a lot of sense. Usually I get my model input from the science team, who runs calculations on how the currents will flow in the coils. And from that I run calculations, simulations. I help the team out with doing the actual force calculations. If we add a little or take away details or metal parts, what it does to the magnetic field. For this analysis, they wanted to find out if it was a problem if they used steel bolts in the vicinity of the bore of the magnet. These steel bolts can distort your magnetic field, and we need to know if they distort them too badly, in which case we need to find another solution. So the first thing I do is I defeature them. See all these cable holes here? They are not really relevant for the simulation. And I also added some simple examples of the steel bolts that I'm simulating here. So once I have that, I put them in the actual model. I build a geometry out of them. And here you see that entire section is modeled. And you see this big disk around it that needs to be included in electromagnetic simulations typically, because the magnetic flux lines have to have space to go back and return and form a closed loop. So here I apply some boundary conditions. I assign materials and I assign loads, and then I run my simulations, once with the bolts and once without. The model runs, it looks like this. What I typically also do in the post-processing is pretty it up. And this nice retro art colored thing that you see here, that is what shows the non-uniformity level, so you can see where the non-uniformities are happening. But you can also see from the range that it's so low that in this case it wasn't a big problem, and we can definitely use those steel bolts in the locations that we want to. On the site that previously housed a large machine, somebody noticed that underneath the concrete there was a large steel beam, and the question was, is that going to be a problem for our new experiment, Tiny Merge? I already had a model for Tiny Merge, so it wasn't a lot of work for me to put that beam in the same model. It turned out that, yes, that beam got magnetized and caused a kind of non-uniformity that was not acceptable for the goals of this machine. What if we move the machine a little bit up, for example? If we could raise the machine, how far do we need to go? I collected all that information, I documented it, I presented it to the team, and then I moved on to my next projects. A couple of days later, I hear a lot of heavy machinery right into the building, a lot of noises, and what happened was they were digging up and excavating that beam from the floor, and that was apparently the decision. And it's pretty awesome that a simulation like that leads to an effect like this. I have this complete model of Polaris. Originally it was meant to calculate the magnetic coupling between the coils so that the electrical team could make more accurate simulations of their electrical circuits. I expanded the model so that you could also calibrate the magnetic diagnostics of the machine. I also found a way to calculate what magnetic forces are acting on the coils in between them. We are now able to set a limit where we say, okay, we cannot go further because now we're jeopardizing the mechanical structure of it.